All right, good day everyone, and welcome to today's webinar from Ascendo Reliability. This is Fred Schenkelberg, and I've been doing these. I just noticed in the recording, this is the 54th time that we've recorded from this platform, so we're probably over 50 webinars over the last 4 or 5 years now that we've been doing it. And some of you, I recognize, have been here all the way through and been to many of these. And as you know, I record them, and so they're available through the Ascendo Reliability website. They're also a podcast, which seems to be getting pretty good traction on the reliability.fm podcast network. And so there's a bunch of good stuff there. But I'm going to dive into today's topic, and let's see if everything else is working great. It looks like sound is working. Mark is here. That's good. Luckily, hopefully that's not bad news why you weren't able to make it, or maybe it was just traffic. Jit and Michael and Hassan and Sean and all kinds of folks are here. So welcome. Really appreciate you showing up today. So most of what I want to talk about today has to deal with variation and the variability of so many things that we deal with on a day-to-day basis. And so if you're making a product, the parts that we make the product from vary. As you know, that no two resistors are exactly 100 ohms. They vary slightly, and sometimes quite a bit, up to say 20% is some of the specifications for it, or more. And mechanical parts have variation in widths and thicknesses and lengths and diameters and uh, um, surface roughness, you name it. There's just about a way, or multiple ways, I'm sure, for just about anything to measure the variation. Now, variation isn't all that bad, and we can deal with that, and that's what makes things like mass production possible. And yet, there's also this variation that occurs outside the design, and it's the things that happen in the weather. Like right now, I'm waiting for a backhoe that's parked outside to start up, and that'll create some variation on the sound on the system here. Uh, that and some stellar jays are going crazy outside, so hopefully the variation of my local environment isn't too much of a problem. Yet our products get used someplace, whether in outer space or in a deep well of oil exploration or under the hood of a car or on your desktop or wherever, and it sees variation in temperatures. For example, today at home, it was fairly cool last night, and we've got some fog rolling in from the ocean, so it's a pretty brisk morning here in Northern California, at least in our area. I think we got into the 50s last night, which makes it great for sleeping, but it's sweater time during the early morning chores around the house and so on. Later today, we expected to get up into the 80s and 90s, and so it'll be a bit different environment. So my equipment in and around the house sees quite a bit of variation on a regular basis. And of course, wherever you are, I'm sure you'll see these kinds of variations, and your products certainly see them. But what we want to do is make sure that the strength, including the variability of the materials and components, is included in the strength of our product such that it's greater than the applied stresses and the range of variability of the stresses that our products see. And if that all works, then the bridge stays up, right? If we stress a product in such a way that it overcomes the strength capability of that particular product, it fails and the bridge falls down. Now, there's lots of different stresses, and there's lots and lots of different things that have to withstand those stresses. And this gets complicated real quick, but we'll just use this concept of that if our product is stronger than the applied stresses, it keeps working. And it's what we're really after when we talk about tolerancing and reliability, the connection to reliability in that. Yeah, Mark, you're exactly right. As strength goes down, it decays or degrades or weakens over time, and sometimes the load increases. The traffic on opening day for the Golden Gate Bridge was probably pretty heavy, but it's probably not as bad as the daily traffic today. And the size of trucks are bigger, the loads we're carrying are bigger. There's just more stress being applied. Temperatures are swinging more. We're just the everything around this structure has changed in the last 50 to 75 years, or however old this thing is. It's probably close to 100 years now, I imagine. But the basic idea here is that we know everything varies, right? Everything varies. But it's only sometimes that we really care about it. And it's part of the design process, and to a large extent, this design for reliability is that we need to pay attention to those things that vary, that will accelerate the degradation of our strength or respond to stresses that occur and immediately fail, or the variations of those things is when the stress strength balance gets out of whack. It's those particular phenomena, the variation of our components and materials, or the understanding of the variability in the environment, are the few that we need to pay attention to. Now, I know I've talked about this topic a number of times, and there's so many different things that vary. But the gist is that in the design team and in the process of creating a design for a product, say a phone or a printer or a car or a rocket, is that we need to understand the variability. And that is what affects reliability, in my mind, as much or more than anything else. Now, many of you know that I often say that it often talk about that it's always the designer's fault. And this is the heart of it. If the design includes clear and useful information about the stress variability and the materials and components variability, they're set up in a better position to actually make a product that's robust and durable and so on. If they don't have that information or are taking shortcuts, then it's likely that we're going to have a product that won't perform as it should. And so I think this is pretty obvious, right? What we're talking about here is pretty common sense. The hard part is in the details of it, of how it actually gets applied. And so I look at it as a couple of, it's like a chicken and the egg problem. We in order to set tolerances on a component, we need to understand its variability. And then to get its variability, we also need to understand that it's stable, that it's a consistent, stable, regular process. And so things like process control and stability of our production facilities for the components and materials we use needs to be in a certain state in order for us to get useful information from it, such that we can set tolerances. But sometimes we need to make the product, right? And create the systems without really that information. And then in which case, then we need to make sure that we have some margin or some way of sorting this out so that we can then set appropriate tolerances and back and forth. So sometimes we create something new, then we start measuring it and find out what its variability is, and then understand its process capability, and so on, back and forth. It goes back and forth. From a reliability point of view, what we're interested in is that conversation happens and that balance is struck such that we still get a functional product, one that we can manufacture with reasonable yields and capability of actually assembling the product, and that it's durable for all of its environmental stresses that it'll see. Okay, so it's back and forth here, right? And some of these basic concepts I know I've talked about before, but this is the one formula that I mentioned in the chat, is this concept of process capability, right? Now, it only is valid in only the CP and CPK numbers and the other capability indices that are out there are only valid for a stable process, right? So we need think of the traditional X bar and R chart or X bar and S chart looking at standard deviations. If that shows a stable process, doesn't necessarily mean that everything is in spec, just that it's stable, that it's the parts, the distribution of parts, dimensions that I get this week are similar to the distribution of parts that I get next week and the week after and so on. And so it's predictable, consistent is the right set of terms. We often don't check that. We ask vendors for their, um, we ask vendors for their process capability, their CPK. Here's our tolerances. What's your capability? And I think that's a bit backwards. That's a bit out of connection there. And the idea, though, is that we should be asking, is your process stable? So if I'm buying a part or creating fabricating a flange, for example, uh, let's get enough parts or similar parts from that manufacturing process so that we can determine, is it a stable process first. Then let's figure out what the appropriate tolerances are such that we get a reasonable CPK and CP. Instead of a designer saying, oh, I need plus or minus 6/10 on this dimension, and then hope that the process is able to make that. I think in many cases, especially for critical parts, it gets a bit out of balance in that it's exacerbated that by our manufacturing processes being located other places than where our designers are. So they don't get that um, intuitive feel and ongoing presence of what the variability is. And so doing a shorthand of just saying, well, what's the CPK, doesn't really help us. Doesn't really help us get the specifications right. Now, one of the things when I first ran into this process capability indices and things like that, I said, oh, and I was a manufacturing engineer, of course. I went right straight to the design team and said, well, you're hammering me and asking me to improve the CPK, the process capability, by reducing the variability of our process. And that's great. I'll do that where I can, yet it's a much easier if you just open up the specification, right? The upper USL and LSL are the upper and lower specification limits. And if those are wider, then I get a better process capability. And they can do it with a design change on a drawing, where in the manufacturing floor, especially the product I was working on at the time, it was exceedingly difficult to squeeze another half ounce of variability out of the process. And so we went to great lengths to reduce variability, but it just was getting more and more expensive. And so I finally sat down with the designer and says, well, where did the specs come from? And it was a resistance value that we were monitoring. And he says, oh, it's just plus or minus 10%. That's what we always use. And I said, well, how does that have any effect on whether this product performs or not? Is it too much or too little, and how do you know? And he had no idea. So it started a whole study to find out what amount of variability actually mattered, which was completely different than reducing the standard deviation term, this 3 sigma part here, this standard deviation, the sigma. And it ended up being that the functioning of the product worked just fine with a much larger specification, or a spec limit, I should say, tolerance on it. And so we were very happy about that. And of course, the effort to continue to reduce the variability never went away. Yeah. And watching some of the discussion here, yeah, you're right. It's not just open it up as much as you can, because it does affect the performance, the fit, form, and functionality of a product. It's got to be done in balance with those other considerations. And we'll come back into some of the issues that come around ways people typically set tolerances. My favorite by far is that you see a design drawing, and in the I want to call it signature block. There's usually a block of the title and units of measure and all kinds of other notes and stuff like that on drawings. And one of them almost always is that if a dimension does not have a tolerance on it, it defaults to plus or minus some number, usually 10% is what I almost always see. And some drawings have absolutely no tolerances on them whatsoever, and it's all default. And I think that is the sign of a very lazy designer. Um, Tolerances are what is permissible for the product to work. Now, on occasion, there are some components and some manufacturing processes, or I shouldn't say manufacturing processes, there are some designs that in order for it to work, for example, the two holes to line up just right, uh, given the way that a product is designed, let's say I've got, let's see if I get my pen to work here. So if I have a hole here, and I'll use just a cross-sectional view of it here, and I've got another part that needs to align with that, they might be offset just slightly because of where these things get attached somewhere off in the distance, and we call it a tolerance stack up, that these two things are not quite lined up perfectly. So if we needed to put a bolt or a screw or something through that, or a flange or a cylinder, it might not quite make it. Now, one of the tricks is to open the size of these holes, right? Make them both a little bit bigger, such that if this one's big enough, this offset could be taken up and I can still uh, put a bolt through it and it still fits. Now, it's a trade-off though, right? Because now this bolt is not as tight to the mating surfaces as maybe we want. And maybe that'll come loose, or it'll create some slop, or it shows up somewhere else as being not quite right. In worst cases, it creates areas for corrosion to occur, it creates small motion is permissible, all kinds of problems can occur. So very quickly it becomes a trade-off. Now, if the designer wants it to be a perfect fit, where the two holes line up absolutely perfectly, and I'm getting some lag here, and they're just the size of the bolt that goes through it, we may end up with a lot of scrap. If they don't fit, we either have to repair it, rebuild it, or throw it away, or do something else with it. And so it becomes a cost if we are not able to assemble it. If it's assemblable, right, with an more open tolerance, it may create paths for failure in the field. So we may improve the yield in manufacturing, but we give up its ability to perform in the field and or to fail eventually. And so this is just a very simple example, but and I'm sure you can think of many others where this balance between how do we set tolerances such that we can still build it and it still works. It is a tricky part of the design process. Now, the part of it that's where we come in is that if we end up with a product that's difficult to build, it's very likely that we're going to end up with more failures that escape the plant, that are not sorted or weeded out or inspected out. They get to the field that have marginal performance. And so that's one path to failure, right? The other path is that we get parts that are easy to assemble and have huge tolerances and allowances for the variability, but then it's just a little bit more rattly. It's a little bit less fit properly. Customers sense that it's not quite as tight as, in using that word loosely to mean of high quality is often a perception when tolerances are very tight and very consistent. And so we end up with either less acceptance of the product, or we allow for more variation within the design to have less ability to withstand the stresses that it sees in the field. And so those couple of concepts are key of why we in the reliability world pay attention to tolerancing. At least we should, right? Now, SPC and process capability and tolerancing are not consistently considered reliability tools. They really should be done by other people and monitored and managed and enhanced by other teams within organizations than strictly a reliability engineer. Now, all too often, we're the representative statistician around, so we end up with paying attention to SPC and working with vendors to reduce the variability of their parts. But you also need to put your nose in to the designer's area and look at the practices of tolerancing, and especially the ones that are critical to the reliability performance of your product, is understanding the variability of the supplying process, the materials or component dimensions that you're putting together, and understand the impact of the stresses, both in manufacturing and in operation and use, and how it impacts the performance of that product. And for the ones that have the stress strength curves that tend to overlap a little bit, there's not much margin there, those are the ones we need to really pay attention to and get right, and work with the design team to get the appropriate tolerances such that we have an appropriate CPK value, process capability, and it functions. And it functions over time and hits the reliability targets. It's an area that is just ripe for reliability folks to interact with the various pieces of our processes and make that all work. All right. So I don't remember that I have any slides on this one, but so how many ways can tolerancing go wrong? Have you seen that before? I know in the past, in my presentations, I usually have my answers for this one. But for those that have gotten involved with tolerancing to one extent or another, um, yeah, multiple ways. Well, what do you mean, Rohit? How many? And Dennis, yeah, what do you mean? And I mentioned that they use just a default. They don't even think about it. I think that's a critical way that it goes wrong. Well, yeah, if manufacturing can't make it, then that's a process capability issue, right? If they're not able to create a product to spec, um, it it's the process. Deming and his philosophy comes to mind here is that if you make a product that can't be built, it's not the manufacturing process fault, right? If I need to keep to very tight tolerances for a process that you want to be as cheap as possible, well, we're just not going to get there. Yeah, just make it small because it sounds good. Yeah, it's always a good reason. I like that. Now remember, process control really is just monitoring the process, right? And we're looking for opportunities to make improvement. Just because we're measuring SPC doesn't mean that the process variability fundamentally changes. It is what it is, and we're just monitoring it. And we're looking for those special causes that are causing it to shift or to change in some uncontrollable way. But if our standard process is plus or minus, 10 mil, and the spec says 2 mil, we're using the wrong assembly process. We have the wrong technique here. Yeah. And David, you're bringing up this idea of the methods that are used to do tolerancing, worst case and root sum squares. I also would add to that list the Monte Carlo process, getting actual distributions of the variability that you're looking for of the various dimensions, and then using Monte Carlo simulation to sort out what your appropriate tolerances are for an appropriate set of fits that you're looking for. Yeah, but worst case is all too often it's the first run because it's the easiest, and if it works functionally with the worst case scenario, if they're making good assumptions or have good data on the amount of variability of parts coming in, that can actually work. But sometimes that tolerance stack up means that if everything's at its worst case, it just won't fit, it won't work. And so they use root mean squared as a technique to get the benefit of averaging. For example, if I have 5 parts that need to line up just perfectly, then if I use the mean values or the averages of those things, I can probably get more of a tolerance to work and lose less pieces rather than using them all at worst case. And so the idea is that the root mean squared gives us the benefit of averaging. Unfortunately, in the production process, it's an individual part that I'm dealing with, right? And so the next better technique is to look at, well, I should also say the root mean squared has this assumption that things are normally distributed, oftentimes. And oftentimes they're not. Parts are binned and sorted, and so they have truncated distributions or skewed distributions or all kinds of variations of patterns of variation, I should say. And so the idea is that we should, as oftentimes the statistician, local stat guy, is say, hey, look, we need to understand the variability of these critical parts. Let's go measure them. And then let's actually use that information without simplifying assumptions. In Monte Carlo simulation, you can do it in Excel. There's even add-ons to do it that way. R has some great packages for it. Then you get way better information about what are the critical dimensions that you really need to pay attention to and which ones can you play with a little bit. Yeah, carte blanche setting them without much thought, setting them because that's what I need independent from what process is actually capable of producing, are all kind of blind ways of doing tolerancing. And so oftentimes the simple thing with all of these is just having the information about the variability of the parts, right? So yeah, and DOE is a good option to balance and put all these things together, and it's a process to go get that information, right? The amount of variability you're dealing with and optimize for it. But even just get some prototypes and start making measurements. You might only get 3 parts. You can calculate a variance with that. It may not be all that terribly accurate for the population, but it's a start, and it's better than just assuming that it's plus or minus 10% of the mean value, or whatever the other techniques may be used. And so hopefully you're getting the notion here that I'm really, really trying to focus on variation. And oftentimes it's our ability to help people understand the magnitude of the variation and the shape of that variation in order for us to have informed decisions on setting tolerances. And so that goes right back to the early piece where it's a chicken and an egg thing. Especially for new designs, we don't know what the variability is, or that we don't have information on this new manufacturing process. We just invented this material. We don't know. We've only made 3 samples. We don't know its variability. Well, then it's a good time to start tracking that information and finding out what variables are most important to keep track of and to understand. It could be a material property, it could be a dimension, it could be its coefficient of thermal expansion, it could be all kinds of things. And so the first real step when we're running through these discussions is to measure, right? Let's get a hold of parts, let's get a hold of processes, let's get the best available data that we can and actually measure it. A part of that is SPC, right? Control charts. What we're looking for in order to set tolerances that aid the entire life cycle, including reliability, Yeah, I think I did spell it wrong. There should be an S in there. A little bit of variability in my spelling, which I know exists. Sorry about that. Um, is Statistical process control just starts the process of measuring it. And let's measure it over time. And our intent is to determine, is it stable, right? Let's figure out, is it a stable process? Is it consistent? And then the standard deviation term from that process is meaningful and can be used in capability indices. If the process is not stable, we need to fix that first, because the ability to measure a standard deviation this week may be pure fiction for what we get next week, and so on. And so it's a critical part of setting tolerances to have a stable process. And we know it's stable by doing control charting and measuring it. The other piece is that we're going to use that standard deviation value to judge how big our tolerances are. It goes back to that CPK kind of measure, the capability indices. We also use it in stress strength calculations when we're comparing the stresses of the environment on the materials we're using, how they age or wear or whatever. That variability is used in so many places that it's often assumed or overlooked, or we just put a random number in there or whatever. It has to come from the data. It has to come from the best available set of measurements that you can get. Yeah, Westinghouse rules. Yeah. I don't know if that was meant to be a pun, Robert, but yeah, there's 7 rules in the control charts. Yep. But also, when they were doing control charting and wrote the book on it, I think they were doing pretty darn good too, and a different definition of rules. Once we start measuring stuff, there's a saying, and I don't remember who said it, is, what gets measured gets done or gets paid attention to. I don't remember the exact quote. But the process is going to be what it is, and we're measuring it. And we want to make intelligent changes to the process to improve its ability to create products. Oftentimes that involves reducing the variability, but I think first is get it stable. Second, reduce the variability, and then third, center the mean value. And those 3 steps in that order allow us then to manage a process and improve its stability over time, improve its capability to meet designers' intent, and give them more latitude for setting tolerances appropriately for the functionality of the product. Now, this seems like, to me, like many, many steps away from reliability. Yet, if we don't measure variability and we're setting tolerances on assumed or fictitious standard deviations, we're going to see it in the product's performance and in its field reliability performance. And so it's one of those steps that we should certainly pay attention to. And then once you go through this process and you find, say, 8 or 10 or however many critical to reliability, quality folks call it critical to quality, variables for our key components that we need to monitor and keep track of over time, then it's a matter of actively monitoring it. The control charting is not done once we know it's stable, is we want to make sure it stays stable. And especially when you're going into high volume production, this monitoring step is critical, because it doesn't take much of a change to throw your process, the variability of that process, out of kilter, such that it starts to show up in your manufacturing process and in your product's performance in the field. And so there's a ton of different pieces here, right? And all of them interact in order for us to create a reliable product. All right, another one of these questions for you. I see a bunch of stuff going on in the chat window. I haven't been keeping up with it. Looks like a couple of conversations, but here's another one for you to throw into the chat. Is How important is the measurement system that you use? And a follow-on or corollary is, how do you know your measurement system is good enough? The MSA, Robert, is the measurement system analysis, right? And gauge R&R, Elena, is a part of a measurement system analysis, right? Anybody know the 5 sources of variability that an MSA would look after? Huh. Mark, I'm not familiar with the delta M, delta P. Precision is one. Um, yeah, repeatability, reproducibility, bias, precision. What's the other one? Now, Robert, those are sources of variability. What are the things we look for in a measurement system to be capable of? One of them is linearity, right? Is the scale, there you go, is it measurements at the low end of the scale as consistent measurement error as measurements at the high end of the scale, or variations of it? Doesn't necessarily mean that the error is a linear function. It might be a parabola when you get into it. Oh, okay. So thanks, Robert. Yeah, it sounds similar to a capability index, but a little bit different measure of it. Yeah, and I've often, instead of like a 6, 7x better, I've often heard of the rule of 10 in that. Um, so there's lots of different ways things can go wrong. Now, in my experience, a gauge R and R, a just measurement, determining the measurement error due to repeatability and reproducibility, uh, often gets you a long way towards understanding if your measurement system is contributing a significant amount of error to your measurement. Now, just about every time I've done this, and when we were saying, well, we're not really sure about this measurement system, is it suitable for what we're trying to do? And let's say we have a tolerance of 10 mils, and I'm using a gauge that contributes 5 mils of error. Would that be a suitable measurement system? It's taking up 50% of the tolerance. No. And you know why, right? If I'm at measuring something that actually is unknown to us, but is actually close to one of the boundaries of our tolerance, the measurement error gives it a pretty good chance of being in or out. And it just clouds or creates a fuzziness around the edges of our measurement system. Yeah, a marginal, as you're right saying, Dennis, is 30% of the tolerance or better. Now here again, I often say, well, let's increase the tolerance if we can. Then our measurement system becomes more capable. Uh, Oftentimes, though, we're just using the wrong gauge altogether. We're using a caliper when we should be using something more precise and more repeatable, for example. So in and apart all of the system is that standard deviation that we're going to use to set tolerances, and we're going to measure and use for stress strength calculations, and that we use for so many other decisions in a design process, is the source of that measurement is something we need to pay attention to, because measurement error becomes an expander, increases that standard deviation. And if we're increasing in it significantly for the size of the decisions we're trying to make, that's a pretty serious problem, because we're just going to have bad data at some point. So for those critical pieces and things that you're going to go measure, use what you have to get started and get an idea where you're at. If the variability in that circumstance is acceptable and you can set appropriate tolerances and have a suitable design and everybody's happy and the part works, you're done. But oftentimes for those critical dimensions and the things that are expected to have very little margin or very tight tolerances for one of many different reasons, then the the idea is to make sure that the measurement system you're using is not ad adversely impacting those decisions. And as time permits, make sure your measurement system works everywhere else as much as you can. And so, yeah, all good stuff there. All right. Circling back a little bit, and it's more of a summary at this point, is that we need to know the variation. Right? In order to get started in setting tolerances and understanding what's important to the field reliability of our part, we need to understand what's going to vary and how much variation it's expected to have. So if I'm drilling a hole in a piece of metal to attach a bolt to it, I'm not only interested in the size of the hole and how consistent it is. It may also be roughness of that hole, and is it actually a circle or is it elongated in some fashion? Um, does it damage the material property around it? So if the drilling process creates heat, it may change the material property of what we're drilling through. Does it change its strength? Does it make it brittle? So as a reliability engineer, we're often looking at our parts and our products and with an eye towards what could fail. And how add to that repertoire is, well, what can vary? So the sharpness of the bit can create more heat and create a hole that's not as round as we would like it to be. It may cut slower also, which would affect manufacturing. So they're often interested in keeping the drill bit sharp. If we're trying to hold tolerances and the manufacturing process itself has got tools that vary, understanding the impact of that variation on our product's performance and on its reliability is a way we naturally start looking at this variation. The other thing that we bring to the table is that if that variability starts to weaken a part, it's that stress strength curve concept. It creates more it doesn't fit as tight, for example, and it's more likely to come loose or create paths for corrosion or increased wear. Those kinds of things are sources of variation that lead to premature product failure. And so it's with that kind of eye that we typically look at variation. Yet, in order to control that variation and understand it in the design of both the manufacturing processes and of the product itself, is that we're dealing with that statistical process control, and we're dealing with the setting of the tolerances. And so we bring to the table an eye towards how variation is bad. And I'm wondering if I spelled variation wrong here. I think I did. Anyway, and then the element is then connecting that poor variation to problems in manufacturing, the adverse effect to product performance for what the design intent is, but then more importantly, how it leads to premature failure. And those are the ones that we circle back then again to the design team and the SPC and measurement systems and so on, and get as good as information as we can get. See, that part of my variability on spelling is I can't tell. I often look at a word and think of the ways I could misspell it, and so when it's right, it looks wrong to me. I'm not a good speller. Working on it, definitely working on it. All right, one thing I got to do is retrain my computer remove all of the misspellings of reliability. I've taught it over the years and saying, yeah, that's good. That's a different story. All right. End of the day, when we're working with a design team and we're in that design for reliability mode, part of our information is to enhance the ability of the designers to set what I call informed tolerances. That they're able to understand that standard deviation and that it's a reasonable estimate. It comes from real data as much as we possibly can get. And here's how, if we're outside of this range, here's how the environmental stresses are going to affect it. Here's the impact it's going to have in manufacturing and yields and so on, which may or may not be a critical consideration. But it's setting those tolerances such that we get a good process capability and a robust product at the end of the day. And it starts with understanding those standard deviations, understanding those variations. And that just takes time to go get those measurements, go find that information, to track and understand it, and then work out in our world, then how does understanding those variations and setting tolerances that account for them allow us to create a more reliable product? We know that the environment's going to have variability in it. And we know that, say, that bolt example, the two pieces of material may shift relative, dimensionally shift relative to each other. The differences in coefficient of thermal expansion, for example, as temperature changes. And if we don't design an appropriate bolt in fitting or attachment method, it could fracture the bolt if we're using too small of a piece. Or it could buckle the material, or it could do all kinds of strange things to our design. Understanding the range of temperatures that we're expected to see is one of those variabilities that the design team needs to understand and use in their calculations of what's the right attachment here. And then let's set tolerances such that we can actually make it, and it accommodates the variability that we're going to see in the field. And often people call that robustness. Robustness then also allows us then to create a product that's more reliable, more durable, and so on. But that's just one source of variability. The other is how does that material change with time? Does it become more brittle? Does it wear? Does it create corrosion paths? All those elements that can cause problems for us. And why we get paid the big bucks is that we sort out, well, which of those is most important in this particular design? And let's make sure those work. Yeah, and I'm glancing over at the chat, and Dennis, yeah, the verification testing. It's often too late to be going after the variability numbers that we need, the standard deviation numbers we need to create a design. Yet it's a good place to make sure that we're on track. It's usually the first place where we're really getting reasonable numbers of samples. And so it's time to prove the concept. All those assumptions made earlier, let's make sure that those standard deviations are what we thought they were. Let's measure them there. Yeah, there's time to go break things and test it and see how it works in different environments. And hopefully we're confirming, verifying everything that we were expecting and not discovering anything new at that point. Right. So in summary, and I think I didn't change the labels on this one. So I'm going to go back go on to the next slide and say, in summary, we need to understand variability. And the big part of that understanding the variability is understanding how it impacts the capability indices that we use in manufacturing. So if we're dealing with a key supplier on a critical dimension of a part, it's not enough to say, hey, you need to hold this tight tolerance. It's a matter of understanding first the variability of their stable process. And then can we design a product that is manufacturable and will fit within the capability of that manufacturer, not the other way around, at least in my opinion. And part of this is, given that so many different things vary, a big part of our role is looking at it through the lens of a reliability engineer, going, well, what variability is important to the durability, the robustness of the product? So what will lead to increased wear? So the high end of the variation of heat, for example, and pressure on two mating surfaces that move relative to each other. That would be an area of concern, that in hot, high pressure situations, we're going to see increased wear. Well, is it too much wear, too fast that it's going to cause problems? But that goes back to part dimensions and sizing and capabilities and eventually back to the tolerancing. And so working closely with your design team by in enhancing their understanding of the standard deviation of the elements that are of most concern to the eventual performance of the product helps us to create a reliable product. And so I, I knew I was going to be a little bit short today, but I only had a couple of key concepts I wanted to talk about. And I'm now going to take a closer look at what's going on in the chat window. Lots of stuff going on there. But I certainly have time for some questions, or if you guys have some other thoughts or concepts here, let's bring those out. And you witnessed my variability in spelling, or my ability to check spelling, I guess. That's probably a big part of it. Sorry about that. All right, a few people are, few folks are typing. Let's see what comes up here. Let me see if there's anything. Eva, I think you got repeatability, reproducibility, bias. Is precision one? Yeah, no worries, Eva. Linearity, stability, that's 6. There might be, I've always thought of it as 5, and I have trouble myself keeping track of them all sometimes. The webinar announcement link. Munir, you can find it over at accendoreliability.com and look underneath events, I believe it is. I don't have a web browser open at the moment. I think it's under events or webinars. I don't remember the menu choice here. Under webinars. And then you can find the Accendo Reliability webinar series in this particular event. And that has the announcement on it. Oh, this Thursday's event. Oh, okay. Yeah, let me see if let me track that down. And that's, thanks for the reminder. This is um, uh, euphemistically, I'm calling it the SPC month here at Accendo Reliability. It's like there is a here or anything like that. But the Stephen Wax he's really got a great program and knowledge about statistical process control, and he's offering a webinar for us that, and here it is. Here's the link for Stephen's presentation this Thursday, and he's going to talk about 10 keys to maximize the benefits of your SPC program. So if you've got one going on, or you need to set one up and do it well, this hour, I think he's probably planning on an hour, hour and a half, and we'll have plenty of time for questions, will be all about SPC. And that reminds me, the other thing is that Stephen has just launched an SPC course. It's a very comprehensive course on statistical process control and process capability, and it goes in way more detail. And as I was recording it with him and going through the editing in it, I kept stopping to take notes because I was learning stuff hand over fist in the whole process. So let me give you the link to that course if you want to check that out. We recently added this to the site as a pretty comprehensive course, and you can get a little bit more information at that link about the course and how to sign up for it and so on. It's a self-paced, online, on-demand course. It's got tons of exercises, and we stopped the recording or the lecture, unlike a webinar where it's pretty much straight off for an hour. Stephen has a really nice technique of stopping and saying, hey, now what do you think about this? You know, what would be a reasonable number here? Or why don't you go calculate this at this point? And then we stop the video and it opens up an exercise slide or a follow-on slide that then says, all right, well, what's your answer? What's your response, whatever. And then it's back into the lecture. So just about every lesson has one or more interactions built into it. And it was just this natural style of his presenting, and then we were able to build that into an online course. So it should be pretty interesting. So, right, a couple of links.